So hi everyone, welcome to today's South American Geometry webinar. If you before we start, let me just remind you that all our talks are recorded. So if you wish to check any of the previously recorded talks, you can find those on our YouTube channel. Also, if you wish to subscribe to our mailing list or appoint yourself to the WhatsApp group, which is strictly for seminar-related announcements, you can follow the instructions on the chat. You can also subscribe directly to the Google Agenda by clicking the last link available, in which case an item will be added to your Google Calendar. You can also subscribe to the email and mailing list by sending the word webinar to our institutional address. So there's many ways to interact with the geometry seminar. Today, we have my colleague here at Unicamp. So very happy to have Lino back on the seminar. So I think it's been 2 years, so it's got some new stories to tell. And today we're going to hear about Kähler-like scalar curvature and homogeneous spaces. Please, Lino, 50 minutes and then a bit of discussion.
Okay. Thank you very much, Enrique, for the warmly introduction, and thank you, the organizers, for inviting me to speak in this webinar. I'm very happy to talk to this lot of colleagues here. And okay, and this is today we talk about this Kähler-like scalar curvature. And then this is a joint work with my colleague Ailton Oliveira in Mato Grosso do Sul state. This is the state of the Pantanal here in Brazil, very near. And okay, let's start with some basic definitions to introduce the topic. Just recall, this a motion Hermitian structure on a even dimensional manifold is a pair with the Riemannian metric G and then almost complex J, such that the J is orthogonal with respect to the metric. And this triple here we call a most Hermitian manifold. In the case J is a complex structure, it's an integrable structure, the pair is a Hermitian structure, just call it Hermitian structure. And in this case, we call this triple by Hermitian manifold. Okay? And if we have a most Hermitian manifold, one can define the fundamental two form, defined by this: omega xy is a G. You put the x in the first entries here, with J. Okay. And non-Hermitian structure, in this case, G must be integrable. An Hermitian structure is scalar if J is parallel with respect to the Levi-Civita connection of J. Okay, this is the I will denote the Levi-Civita connection of the Riemannian metric by D. Okay, and in this case, parallel means this. And we have some classic result. This non-Hermitian structure is scalar if and only if the fundamental two form is closed. In this case, we have some of the three geometric structure here. It's a symplectic structure, it's a complex structure, and a Riemann structure. All three are combined. Okay. Before actually, I prefer to make some quick review of the Greyer-Vela classification of almost Hermitian structures. Okay, this is a very classic topic, very interesting. We start with the almost Hermitian manifold and the omega, the fundamental two form. And the key idea here is understanding the symmetries of this three tensor. covariant derivative of the fundamental two form. Okay, and I just put the steps here. We consider V real vector space of even dimension. J the almost complex structure of V. This is just an endomorphism. J V to V, J square is a minus identity. Okay. And then compatible, and then put some scalar product compatible with J in this sense. And we denote by this W, capital W, the subspace of this V star, tensor V star, tensor V star, defined by this property. Okay. This will be skew symmetric in this last two entries. Okay, and we have this kind of the symmetry here. There's an orthogonal here, is a skew orthogonal in this last two entries. Okay, in this case, alpha will be these three tensors satisfies this. Okay. And now we define the following subspace of W, the capital W. W1 will be this. This will be these three tensors is a skew symmetric with respect to this, the two first entries. W2, the three tensors satisfies this relation, is a permutation. WT3 with this relation. Well, alpha bar is like a trace here, this trace. And W4 is a little bit bigger expression, but okay. And we have this theorem of Gray-Ervela. It's a very classic. The subspace W, I can split it in this space in four subspace as direct sum, and this is preserved by the UN action induced by the linear action on the vector space. And each component Wi is irreducible with respect to the representation induced by the unitary group. And now, for the classification of the almost Hermitian structures, we take this machinery and take alpha as the covariant derivative of the fundamental two form. Okay, and we have some, for instance, some examples of almost Hermitian structures. The class of 0 is the Kähler structure. W1 is nearly Kähler. This is very well. This is a lot of study of this structure. What means this, for instance? W1. This means the variant derivative of the omega satisfies this. This is a now almost complex structure is nearly Kähler if is skew symmetric with respect to these two first entries. Okay, and then and so on. We have W2 almost Kähler, W2 semi-Kähler Hermitian, W4 LCK manifold, locally conformal Kähler, and a W1 plus W2 1-2 symplectic. And then this depends on how to split in your tensor, the covariant derivative of the fundamental two form, where PC where fitting the it. We have 16 classes. Okay. Just some remarks. Semi-Kähler is a omega is co-closed. Nearly Kähler is this. I just say 1-2 symplectic, or disappear in the literature as quasi-Kähler. Write this way. This is the derivative of omega is 0 if you took x10 type and the two vectors type is 0, 1. Okay. And then this is the classification of the almost Hermitian structure. Okay. Very good. A linear connection on a M is called Hermitian if the connection preserves the metric and the almost complex structure, in this sense. Okay, this is important. We are not assuming that J is integrable. Okay, and given an almost Hermitian manifold, there is a unique connection, nabla, that satisfies this condition. This is a Hermitian, and the 1-1 part of the torsion vanish. This connection was introduced by Hermitian and Oliveira, and in complex case, if J is integrable, this connection coincides with the Chern connection and on a Hermitian manifold. And in the literature, this connection nabla is also called Chern connection. This is a abuse, okay? Or, for instance, in some works, appear as canonical connection. Okay, and but because the Chern connection, the connection used by Chern is appear in the holomorphic setup, in the complex setup. Okay, this is coincide with the Chern connection in this Hermitian case, in the integrable case, but we are not assuming the J is integrable. And we define the Chern scalar curvature, the Chern, the scalar curvature of this Chern connection in the very standard sense. We take some unitary frame and took this summons here, and it's a very standard result here. If it is a very well known. If M is a Kähler structure here, then we have the S, the Riemannian scalar curvature, is equal to 2 times the Chern scalar curvature. Okay. And Dabkovsky and Locke suggest a name for this. The Hermitian matrix satisfying this equation, this guy is called Kähler-like scalar, Kähler-like scalar curvature. Okay, and now we can ask ourselves if we have some almost Hermitian structure, non-Kähler, okay, non-Kähler, that satisfies this equation. Okay, I will show you some examples. Okay, the first example is a very interesting result. This is a very nice result from Gauduchon. And if we start with a closed Hermitian manifold, and if we assume the Riemannian and then the Chern, twice the Chern, scalar curvature, in average over M are equal, then this manifold must be Kähler. Okay, and if you have this, not necessarily equal, but in average are equal, this force this Hermitian manifold to be Kähler. Okay. If we start with a nearly Kähler manifold and impose this condition, then these two, Lichimi and Meyer, in 2020, proved this force this almost Hermitian structure to be Kähler. And if you have almost Kähler manifold, almost Kähler, because it's the stereo derivative of the two form, the two form is closed. The fundamental two form is closed, but J not be integrable. But if you start with this almost Hermitian structure like this and impose this condition, the conclusion, the structure must be Kähler. Again, very recently, if the pair, if the almost Hermitian structure belongs to this Grama class, and if you impose this condition, then the structure must be Kähler.
Lino, can I ask a quick question?
Sure.
So about the first statement, so this is saying about Gauduchon, right?
The
so
first is for Gauduchon.
Yeah. So this is saying that the only interesting remaining cases are non-compact, right?
Or you have no Hermitian, because look, this is a Hermitian manifold. If you start with the complex structure, this is the point. This is the point. Okay.
Okay. So remind me. So Hermitian here.
Hermitian is integrable.
Okay. That's fine. Okay, thank you. Okay, that's good. Yeah. Okay.
Okay. And then actually, and again, very recently, note this difference here. Okay. Now we start. If you start with dimension 4, and now almost Hermitian, and impose this condition, then the manifold must be Kähler. Okay.
Right. That's weaker.
But this is for dimension 4. Okay. And now this is
here. Up Meyer here is Marcus.
Okay.
Is it?
Sorry, say it again.
The author here, Up Meyer, is it Marcus Up Meyer?
Yeah.
Okay. I didn't know he was studying this. Okay.
Okay. All these examples suggest us the following question. Okay. Do close almost Hermitian non-Kähler manifold of real dimension greater than 4 satisfying this condition exist? Because our example, if you impose this, if you start with the Hermitian or maybe almost Hermitian and impose this condition that this is equality, this forces the structure to be K. But that is some example we call a non-Kähler, and almost Hermitian satisfies this. Okay, and we search for this Kähler-like scalar curvature on generalized flag manifolds, but we put some additional hypotheses here that's just in the invariant almost Hermitian structure. Okay. Okay, let me now just describe a little bit this generalized flag manifolds very quickly, just to fix some notation. And just start with quick review on homogeneous space. We start with the manifold M with the transitive action, and I fix a point P and consider H the isotropy subgroup, and M is different to this coset space. And the action of M induces homomorphism. And at the infinitesimal level, we have this homomorphism of the algebra. And at the point P, we call this the origin of the homogeneous space. We have this surjective map with kernel H, the Lie algebra of the isotropy subgroup. And we denote this M by this quotient space, and identify the tangent space at the origin with this subspace. Now we define the isotropy representation of the isotope group on the tangent space after the origin, given by the differential of this phi is the action at some point in the isotropy, because since the isotropy fixed this point P, this is well defined. Okay. And we call homogeneous spaces reductive if we have this split of the Lie algebra and with this condition. Okay. And in this case, for the reductive homogeneous space, the isotropy representation is equivalent as representation to this endomorphism. Okay, and now we work in this setup. And in homogeneous space, or in this theory, we consider the G invariant tensors on the manifold. Okay, this is Riemannian metric, almost complex structures, all tensors. G invariant are the one correspondence with H invariant tensors here, or also one correspondence between the adjunct H invariant tensors on this subspace. For instance, on homogeneous space, and G invariant matrices are one correspondence with scalar products on M invariant by this action. K forms is the same. Invariant almost complex structures are endomorphism on this space satisfying this condition, and invariant by this action. Okay. Etc. Okay. Now, just to fix the notation about the generalized flag manifold, we start with the complex simple Lie group, and then take P, a parabolic subgroup, and G, the maximal compact subgroup. I'll give you an example in a second. And denoted by K, this intersection. Generalized flag manifold is this homogeneous space. This is this is a identification here. It's not needed to build this, but in this case we have this. This is very nice because this side tells this manifold is compact, and this side tells this manifold is complex. Okay. We have compact, complex, homogeneous space. This class is widely studied in the For instance, a compact Hermitian symmetric spaces are flag manifolds. Twistor space over symmetric spaces are flag manifolds. And projectivization of tangent bundle of sphere, some symmetric space are flag manifolds, and so on. So on. Okay. If just recall, a parabolic group is a subgroup that contains the Borel subgroup. But in the case the parabolic is the Borel subgroup, in this case we have this intersection is the maximal torus, and this homogeneous space is called a full flag manifold or maximal flag manifold. And just on a slide in root system, we start with the Lie algebra of the complex group, fix H in a Cartan subalgebra, and denoted by capital pi in Greek, the root system of this pair, and by sigma, the set of simple roots. And we can decompose the Lie algebra, the complex Lie algebra, as follows. We can put the Cartan subalgebra and some with one dimension complex subspace. Now this is very important actually. For each subset in the set of simple roots, we can define a parabolic subalgebra in the following way. The parabolic will be this part, the same as the Cartan subalgebra, but plus the sum of all root spaces in the for negative roots, plus the this roots alpha in the set of roots spanned by this subset of simple roots. Recall the simple roots is like a base of the all roots. I can write all positive roots in terms of a combination of simple roots. But now we just consider a part of these positive roots. And we have like just a simple draw is in the matrix. We have this part is the diagonal. Here is above this diagonal. Here will be some parts of the matrix. Okay. And for the choice of the theta, we define the generalized flag manifolds associated to theta. It's just this coset space. Okay. And just to mention, the flag manifold is a reductive homogeneous space. Okay. And this is an important feature. Here is the isotropy representation of a generalized flag manifolds. Okay, in this case, recall this M will be identified the tangent space at the origin of this homogeneous space, and we can decompose this vector space in the sum, where each Mi is a reducible component and non-equivalent with respect to the isotropy representation. Okay. Now we can describe the set of invariant matrices on a flag manifold. Recall, G invariant matrix is just a scalar product invariant with respect to this representation. We have this. Actually, this will be negative of the Cartan killing form, but as you know, in a complex simple the algebra, the negative the Cartan killing form is negative definite. We just put in the minus. Okay. This is a scalar product. Okay. And this lambda, capital lambda, is a symmetric and a positive operator. This condition, the invariance, will impose some restriction to the operator lambda. It's not just a positive or a linear operator on M. I need to put some additional condition to obtain this invariance. In this case, we can show that for each reducible component, lambda restricted to each reducible component will operate as a multiple of the identity on this space. Okay, and in this case we have this lambda will be a diagonal operator, and we will repeat lambda 1, this dimensional times, and so on, etc. here. But for notation, we abuse the notation, and we denote the invariant metric just for this number, just for R numbers, where R is the number of irreducible components. Because we repeat, okay? Let's just collect this R numbers. Okay, real positive numbers. In this case, for the flag manifold, the set parameterizes the invariant Riemannian matrix. For invariant almost complex structures, recall on an invariant almost complex structure is this endomorphism. J square is minus identity, and you need to impose this condition of invariance by the adjoint action. And again, J restricted to each component must be a multiple of the identity. And the condition J square is minus identity imply this multiple must be plus or minus the unitary, imaginary unity, the imaginary unity. And we have this. J will be this diagonal, where this epsilon I is plus or minus 1. Okay. And again, we will abuse the notation, and we will denote the invariant almost complex structure on a flag manifold just by a R upper of sinus, plus or minus 1, because this will determine completely this endomorphism, etc. Okay, just put some more concrete example. We can consider the 6-dimensional flag manifold SU3 over maximal torus. This homogeneous space, for this homogeneous space, the M, the tangent space, we decompose in the three pieces, okay? Where each piece have a dimension 2. And non-invariant metric in this case is just 3 numbers, 3 positive numbers. Recall, but they have the dimension 6. Lambda 1, 2 times, lambda 2, 2 times, and that's it. And invariant almost complex structure, J will be 3 sinus, plus or minus 1. And how is the invariant almost Hermitian structure on this space? For instance, if you take the metric G is 1 to 1 and J all plus, we have this pair is scalar. If you have the semi-metric, but you change the sign on here, we have this pair is nearly scalar, and so on. But for all full flag manifolds, the classification of this pair on G over T is due to Luis San Martin and Caio Negreiros. What means the classification? Given a pair, we can decide how to put this in the 16th class or of the Grama classification, but not all class appears in the classification. But it's very, very nice, very interesting result. And then now we analyze this equation in this setup. Okay. Oops. Okay. For we choose a flag manifold and then put some invariant almost Hermitian structure. This is but it's not all flag manifolds, unfortunately, because this family of generalized flag manifolds are parameterized by the number of the irreducible components. Okay, and in this talk and for this work, we made the analysis by the flag manifold with 2 and 3 isotropy components. Okay. What is our strategy? Okay. Very recently, Fu and Zhou provide a formula for the scalar, the Chern scalar curvature, and then we adapt this to our situation, and then we can write this function, this scalar curvature, in terms of these pieces, the 4 pieces actually, and this pieces is related to the almost Hermitian geometry of the manifold. Okay, and then we have this is symmetric part of the homogeneous tensor. D omega plus is a primitive 1, 2 plus 2 on part of the omega. Alpha omega is a Lie form. We can describe this each piece just in terms of the metric and the almost complex structure. Okay. Just for instance, we analyze each term of this formula in the case of flag manifolds. And then we use tools for Lie theory. Okay, we take a flag manifold, an invariant metric, and an almost complex structure. And for instance, this piece here, we can describe this like by this number. Okay, and this is the structure constant on the algebra, and this is we consider trippy of roots that the sum is 0. We need to sum of all these 3. And for the Riemannian scalar curvature, this is a very famous formula available in the literature by Brasilia. And now we need to combine all these pieces, and okay, we arrive in a system of equations, and we need to try to solve this, and put the solution in the some gray value classification. Okay, but the more the lot. This is not so simple to analyze, because if you fix just one example of manifold, you try to compute, you can do this. But to make all family at the same time is not so. It's a little bit tricky. Okay. How can we parameterize the set of flag manifolds with two isotropy components? Okay, we are interested in this case with flag manifolds and the tangent space split into two pieces. There is a recipe to do this. Recall the height of the simple root is the integer that appear in the as coefficient in the eigenvalue root. Okay, we have the eigenvalue root. Is the set that you just pick the CP, the coefficient of the root alpha p. Okay, and this is all parameterized by Avarnito-Yorgos and Pisicos. This set, the flag manifolds are parameterized by this set theta, subset of simple roots, such that theta will be the complement of inside the set of simple roots, just one root alpha p, such that the h is 2. Okay? This is some examples. For instance, you have the E6. If you choose this root, this number is the coefficient in the maximal root. Okay, the eigenvalue root. Sorry. Okay, this root alpha is a 1, 2, 3, 2, 2. Okay, if you take this alpha, we have this flag manifold. But okay, if you have this, it's another flag manifold. Okay? These are for this happens here in the flag of the exceptional group exceptional the group F4. If we start with this root, we have this flag manifold. But if we start with this root, we have another flag manifold. But this is just you need to write all the linking diagrams and make the classification. This is the table. Okay. This is a very worth to point out here. It is because we try to adopt the strategy for all manifolds at the same time. Okay. This is the list of flag manifold. This is three infinite family here, and then for the exceptional Lie groups, and then we have our theorem. If we start with a flag manifold with two isotropy components, denote the invariant metric by this pair, these two numbers, two positive numbers. Okay, and if we force this equation to Chern scalar curvature is equal to Riemannian scalar curvature. If this equation holds, then we have the following condition. In the case this invariant almost complex is parameterized by these two signs, this is actually an integrable complex structure. Then the metric is parameterized by this. Okay. In this case, we have it. This pair is scalar, but it's more. It's Einstein also. But this is Gauss-Schall. Okay. This is not new. Nothing new here. Okay. Just a slight remark, because the Einstein metric is in this family of flag manifolds is already classified by Nathan Silva, Caio Negreiros, Nir Cohen, okay, but also by our Yorgos and Principos. Okay? But this is Gauduchon. Okay? And if you have this almost complex structure, this is not integrable anymore. But we have solution. Okay? And in this case, this pair belongs to W1 plus W2. Okay, this is not trivial solution. Okay, this is a solution. It's a non-Kähler solution. Okay? This works for all these manifolds. Okay. Now with 3 components. For 3 components, we have 2 subfamilies now. One is very similar to the 2 components, but we need to pick a simple root with height 3. Or we need to pick 2 simple roots with height 1. Okay, we call this type 1, type 2 subfamily. And just a remark, we have the number of invariant almost complex structure up to conjugation, because we identify the conjugate almost complex structure, are 2 power 2, is a 4. We have 4 invariant almost complex structure. But recall, a flag manifold is a complex manifold. Actually, it's a Kähler manifold. And then we have at least one is integral, but that is a little bit more. Just an example here, for instance, G2 over U2, you pick this root here. There's a height 3. For flag manifold of F4, we pick this. Okay, this is a type 1, but for type 2, you need to pick 2 roots with height 1, like this. For instance, the Wallach manifold SU3 over T2 belongs in this family. Or you have some exceptional example here. Again, this is classified by Kimura. This is the list of family of type 1. This is D1, D2, D3 is the dimension of each component. Oops. And we have 3 families of manifolds of type 2. Okay. This behaves in very different way. Okay. Now I will state some 4 theorems, but one for each almost complex structure. Okay. If I put this J1, this is integrable. This is integrable. Almost complex structure, invariant, and then now I pick the Riemannian metric with 3 positive numbers. Okay, and I impose this condition. This holds the metric satisfies the following condition. Okay, for type 1 and for type 2, this is Gauduchon, not new here, nothing new here. This is Gauduchon because this is complex, actually. But we know the classification of the Einstein matrices on this space. And I don't know, coincidentally, when you solve this equation, we arrive at this scalar, okay, and a little bit more, Kähler-Einstein. It's the same case, in the both cases, okay? Now, if you choose this almost complex structure, but now we have some difference here, because for type 2, this is integrable, and then for type 1, this is not integrable. And now we have some, we parameterize lots of families of solution. Here is not new. This is Gauduchon again. But this is a no Kähler solution. And we have here this Grama classification. We have examples in W1 plus W2, W1 plus W3, W1 plus W2 plus W3. This L and K here appear. This depends on the specific flag manifold. This is depending on for each flag. This is a kind of the invariant of the algebra, the simple algebra that appears in the flag. Okay? But this is computable. And then the same game here. This again, J3 is another invariant almost complex structure. This is integrable for the type 2. Again, we arrive in the Kähler. A posteriori, we discovered this is Einstein also. And for type 1 is not integrable. And we have lots of examples. And this is, of course, this is the dimension here is very high. Okay? And the last one here, in this case, is no integrable in both cases. In the type 1, type 2, neither of these is integrable. And then we have some, here we have solution in W1 plus W2 class. And here we have another family of solution. Okay. And this is just this summary of these results. Integrable here means that the Gauduchon is no new. Okay. But in a no integrable case, we can find no Kähler solution. Okay. And okay, I guess this is I prepare for today. Thank you for your attention. That's it.
Thank you. Okay, we have time for questions. Please raise your hand. There's a lot of people in the room. Have you got questions for Lino? Any questions? If not, maybe I have a question. Adriana, you're talking?
Yes, now I'm talking.
Okay.
Does it make sense to state the same problem but changing the Hermitian connection? Or this is particularly important, the Chern connection, by the same reason?
Yeah, actually, theoretically, for the investigation, I guess yes, but because this is a relation with, for instance, the Chern-Yamabe problem, because of the scalar curvature. Okay, you have some imitate some techniques for the Yamabe or Kasdan-Warner problem to this complex setup. But
okay.
I don't know if you in the other connection you have some curvature. Of course, you have put some scalar curvature for this connection, but
yes,
I don't know if there's another meaning for the geometrically meaning, because this is try to imitate the Kähler word.
Okay, great.
Because in the Kähler we have this the two connection identify, right? The Chern connection and the Riemannian connection. And this is how can I use some techniques from Kähler from a non-Kähler word? I guess this is the philosophy.
Okay.
But theoretically, yes, because
it could be done, yes, but we don't know if it has
for instance, I guess you're working with lots of connection. If there is some lots of geometric meaning, but maybe try to investigate this.
Okay, thank you.
I suppose you could have a Kähler-like problems.
Yeah.
For instance, ask for a connection that preserves G and J, but has a different relation with the torsion. You know,
No, I didn't see this. I didn't
Right.
see.
But you could in principle think of that. Right. It's unique if you ask that the one part of torsion is trivial. But you could maybe have Kähler-like problems in the sense that you explore this freedom.
I see.
Kähler-like squared or something. Right?
Yeah. I see.
But thanks for the question, Elian. But I only said this because then you could still do like Yamabe type description. Right? Yamabe doesn't care about the one part of torsion, right? You could just formulate the same type of a sort of analytic approach. So that would make sense. I don't know if that's interesting. If you can prove these Gauge-Chern type theorems for like just by asking the connection to be compatible with the G and J, rather than
that's too general. You have to impose some extra restrictions, maybe.
Right. Maybe you can find a natural condition on the one.
Yes, you have, for instance, the bismuth connection, but only for the Hermitian case. But I don't know what happens with this problem.
Right. You have other natural connections. In fact, you have a degree of freedom of natural connection, which is compatible with a given structure, right? That's what Bryant wrote in his notes. So that's why I'm saying maybe there's a class of Kähler-like problems, but then you would have to prove a Gauge-Chern-like theorem to motivate. I think this is the right. This is how you have the discretion, right? You have to prove a Gauge-Chern.
I don't know. Maybe Adrian, do you think this kind of Gauge-Chern-like theorem for the Weismann connection will be?
No, I don't know. I think that the Yamabe problem was studied also for bismuth, but I don't recall any result now.
I see. But there is some kind of Gauge-Chern theorem. If you take some scalar curvature of
no, I don't know. I don't know. I don't recall now.
Bismuth imposes some condition. This force to be integrable. I don't know.
No, I don't know.
Yeah, I think that's the sanity check, right? If you can prove a Gauge-Chern-like theorem, then this probably deserves to be. You open up a field of Kähler-like problems. I mean, I'd love to just to have a paper called Kähler-like manifolds. But are there any more questions for Lina? So, Maria Laura?
Yes, I do have one question. Will you consider the case when you have more irreducible subspaces for the isotropy representation?
No.
Or is it?
No. But this is just for technical problem.
Okay.
You can do. Yeah. Because the complexity increases when you grow the number of components. Okay. For instance, I guess for the four components, this is a little bit. We can do this, but for more than 4, there is almost nothing. Is no for this. For instance, metric is etc. There is not well understood. But this is just the computational issue. No, theoretically, is the same. But,
yeah. Okay. Thank you.
Thank you.
Any more comments, questions? Well, then I have a last question, yes. So I wrote the question down in the beginning of your talk, but then maybe you gave me the answer towards the end. Because you mentioned the equation for the scalar curvature produced by Fu.
Sorry, say it again. Produced by?
You mentioned the expression for the scalar curvature, which was found by Fu.
Ah, okay.
Right?
Yeah.
Fu and Li or something. Yeah.
Just a second. Yeah.
That one. Yeah. Fu and Zhao. Yeah.
Yeah.
Right. So if that's the case, then the answer to my question is probably yes. But the standard non-Kähler example I know in like 6 dimensions is given by these torus vibrations over K3 surface, which was studied by Fu and Yao.
Okay, example of this situation?
No, examples of non-Kähler.
Ah, okay.
Right. So the sort of my standard working example of non-Kähler situations is the full Yao construction, right?
In dimension 6?
In dimension 6, yeah.
Oh, my standard example is a SU3 over 2. This is a 6-dimensional Kähler. But okay.
Because you like flags, I like vibration. Yeah, it's
Okay.
another story. Again, but the point still being, you're right. So this is a non-homogeneous situation. So my question sort of transcends the methods you're advocating, and I just really want to know: is this problem understood on? Do you know if this is understood for these full Yao 6 manifolds? Is that where the problem originated?
I don't know. Because I actually in the previous paper, joined with Ailton also, we are interested in 6-dimensional because will be the smallest complex dimension, and we can produce examples in dimension 6, but in this flag manifold. But I guess you're asking for another family of examples, no homogeneous. Yeah, this is I guess this is not no.
So yeah, if this, I mean, these are known as full Yao non-Kähler 6 manifolds, and I know they are not homogeneous manifolds; they're not flags. So the methods would be completely different. But I suspect, since Fu wrote this down, and it's the same Fu, I guess. Maybe those are where this problem originated. So I would want to know: does the equation hold? Does the scalar curvature condition hold on? On these 4 Yao manifolds?
Yeah, right. Yeah.
Right. It would be maybe nice to know.
Yeah. Absolutely. Absolutely. Yes.
Yeah. And can one maybe generalize the problem for T2 fibrations in general over some collab Yao, for instance?
Yeah, sure. Lots to talk. Lots of work to talk. Yeah.
We should talk. Yeah. Interesting.
Yeah.
So thank you, Lino. Okay, if there are no further questions for the speaker, can we please thank him again? Okay.